Can you see my presentation now?
Yes, we see now. Well,
Okay, thank you, Branko. Sorry about the interruption. Today, I want to talk about, or I want to present the results of my preprint titled Non-Archimedean Statistical Field Theory. This preprint is already available in the archives. In this paper, I construct, in a rigorous mathematical way, interacting quantum field theories over p-Adic space-time in arbitrary dimension. I provide a large family of energy functionals admitting natural discretizations in finite dimensional vector spaces such that this partition function can be rigorously defined as a limit of dimensioning discretizations. In other words, the final goal of my paper is to construct this measure in the p-Adic framework. Okay, the key fact is that the space of test function is essentially a countable union of finite dimensional spaces. DL is a finite dimensional spaces. Then every test function has a natural discretization. The point is that this key fact is not true for the real Schwarz space. Now, discrete, in my talk, discrete means that the source it belongs to this finite dimensional space at this integral. The domain of the integration is a finite dimensional space. In this case, there is a cutoff. All the test functions in this space are supported in the ball with center at the origin and radius p to the r. Continuous means that the source is a general test function. In this case, in the definition of the generating functional, we integrate over the space of test functions. In this case, we are integrating over an infinite dimensional vector space. In this case, there is no cutoff, but the fields still have a natural discretization. Okay, so the purpose of my work is to understand this limit. This is a discrete version of the generated functional, and this is the continuous version of the generated functional. My main result is the construction of a measure on a function space such that this generating functional makes mathematical sense. And the calculations of the endpoint correlation functions can be carried out using perturbation expansions via functional derivatives, like in the classical case. My results include four theories. In this case, these functionals can be interpreted as a Landau-Gisborne functional of a continuous Ising model. This is a continuous Ising model means that the range of these functions is R. And in this case, J is the external magnetic field. Now, if J is 0, then this functional is invariant under this transformation. Then I show that the system attached to discrete versions of this functional have a spontaneous breaking of symmetry when the temperature T is less than the critical temperature. Okay, this is the action of the energy functional. This is the kinetic term. In the kinetic term, the operator W plays the role of the Laplacian. In the non-Archimedean case, there is no canonical way of choosing a Laplacian. Now, this is the source term, this is the mass term, and this is the interaction term. The W operator is a subreferential operator with a singularity at the origin. This means that this function vanishes only at the origin. This operator is non-local. Then this action is a non-local, is non-local. Okay, an important example of the W operator is the Vladimir-Tableson operator. This is the Vladimir-Tableson operator. We are working in dimension n. This operator is a subdifferential operator. This is the symbol. In dimension 1, and in this particular case, where the dimension is 1 and beta is 1, the action that I already showed contains, as a particular case, this action. this action appears in the p-Adic string theory. More precisely, it is possible to derive the Koba-Nielsen string amplitudes by using general principle, starting with this action. This is the paper, the classical paper about this result. Okay, an interesting observation that all the results presented in my article are valid if Q is replaced by any non-Archimedean local field. Okay, this is the definition. Here you have the definition of the W operator. This is an integral operator on arbitrary dimension. Phi is a test function. The kernel of this operator, W, is a radial function satisfying this condition. Basically, this condition says that the kernel of this operator is an elliptic function. The operator W is pseudo-referential. This is the symbol of this operator. Then I'm going to use two notations. This W delta is this integral operator, and this is the notation for the pseudo-referential operators. These two operators agree on the space of test functions. Okay, in order to construct a discretization of a function, the first step is to fix a truncation scheme for p-Adic numbers. I use this scheme. In this scheme, the truncation is carried out by fixing a non-negative integer L. Okay, so this is the truncation of a p-Adic number. Any number of this form is an element of this group. This is a finite additive group. Now, the space dl is an R vector space, and the functions in this space have this form, okay? I is an element of this group GL, phi r is a real number, and capital omega is the characteristic function of this ball. Now, all these functions are supported on this ball, okay? And this family, the omega functions, are a basis of this vector space. Then I'm going to identify a function in the space dl with this column vector. In other words, the phi I are the coordinates of the space dl. Okay, let me give you an example. Let us consider this functional. This is the function. If we want to find a discretization of this functional, we have to restrict this functional to the space dl. Then this function takes this form. The computation of the n power of this function is given by this formula. Notice that this is a consequence of the fact that all the supports of these functions are disjoint. Then we integrate, and the integral of the omega with respect to higher measure is just p to the minus ln. So this sum is the discretization of this operator. Now I'm going to consider this energy functional of this action. Zero means that there is no interaction. Okay, this is the kinetic term, and this is the mass term. I am assuming that these two numbers are non-negative real numbers. For this reason, this functional is non-negative. Okay. Now the next step is to compute the restriction of this functional to this space. I'm going to use this notation to the restriction of E0 to the space dl. Okay, this is the result. The restriction of this energy functional to the space dl is just a quadratic form in the variable phi I, phi j. These numbers, these are the entries of a matrix, this matrix U. Here you have the definition of this matrix. The matrix U is symmetric, symmetric and positive definite. Okay, then this matrix is diagonalizable and invertible. The important thing, or one important thing, is that it is not possible, sorry, it is, my goodness. Sorry. It is not easy to compute the inverse of this matrix U. in the coordinate space. This is the representation, or better, this is a discretization of this energy functional in the coordinate space. Now, to give a discretization of energy functionals in the momenta space, I need the Lysorkin spaces of the second kind. This is the definition of the Lysorkin space of the second kind. The Lysorkin space of the second kind consists of test functions with average 0. This is a complex space. I use this symbol to denote the real counterpart. Now, the space FL consists of all the Fourier transforms of the Lysorkin functions. Notice that in terms of the Fourier transform, this condition is equivalent to this condition. The dual space, L prime of the Lysorkin space, is the p-Adic Lysorkin space of distribution of second kind. Okay. Now, this is the discrete version of the p-Adic Lysorkin space. Any function in this space has a representation of this form. The phi I are complex numbers, and this condition says that the average of the function phi is 0. This is the real counterpart of this space. Now, the Fourier the set of all Fourier transforms of the functions in this space is the function is the space FL. This is the definition of this space. Now, this condition is exactly this condition. The Fourier transform gives an isomorphism between these two spaces.
Oui.
Yes.
Allô. Oui.
Do you have somebody has a question?
Oui, bonsoir.
Comment ça va, monsieur Diarra?
Ça va, et vous-même?
Ça va, je suis au Cameroun actuellement, je vous appelle avec le téléphone portable.
Oui,
Please
oui,
take off the microphone.
J'ai vu que c'était un numéro que je ne connaissais pas trop.
Oui.
D'accord. Et il faudrait la voix, je ne la reconnais pas bien, c'est pas Dame.
C'est Mamadou, je l'ai connu au Mali. Mamadou.
Professor Diarra, turn off your microphone, please.
Dame Dalai.
Please stop your microphone.
Pour mettre les choses honnêtes, Dame Dalai, vous êtes, parce que tout de suite, je ne vous remets pas, hein, pour dire la vérité.
Oui.
Moi, je suis Bertin Diarra.
Listen, can you stop him?
D'accord. Vous êtes en voyage d'affaires, de recherche là-bas?
Wilson, as a host, I think you can mute anybody.
I'm trying to stop.
D'accord. Vous étiez venu.
Okay.
Okay, please continue.
Okay, so I was saying that this is the discrete version of the Lysorkin space, and this is the Fourier transform of this Lysorkin space. Okay, now this is the energy functional that we are considering. Now minus W delta is this pseudo-differential operator. By passing to the Fourier transform, we get this expression. Now, if we assume that this function belongs to this finite dimensional space, we get this expression, we get this sum. The important thing is that this expression is valid for a test function in this space. Now, if phi is a Lysorkin function, then the Fourier transform of the function phi at the origin is 0. Then this term disappears, and we get this quadratic form. Okay. Notice that this is a quadratic form in phi 1 hat and phi 2 hat. Okay. Indeed, this is a diagonal quadratic form. Now I'm going to describe the matrix of this diagonal quadratic form. Okay. Now, I am working with real valued functions. Then the Fourier transform of any real valued function satisfy this condition. This implies that phi1 hat is an even function and phi2 hat is an odd function. Then these parameters phi1 hat and phi2 hat are not linearly independent. Here, this expression contains the right parameters. I mean, the parameters phi r hat appearing in this formula are all linearly independent. So these coordinates or these parameters are divided into two groups, first group and second group. So this expression is a sum of two quadratic forms. But you see this expression, the matrix is the same. Now I'm going to show you the matrix of this diagonal form. This is the matrix. B is the matrix of the diagonal form. This matrix consists of two blocks, B1 and B2, and these two blocks are identical. Okay, these two blocks are identical, and here you have the definition of this block. Notice that this is a diagonal matrix, and if the mass is different from 0, then we can compute the inverse of this matrix immediately. Okay, this is the result. The discretization of the functional E0 in the momenta space is a diagonal quadratic form in these variables, okay? It is important to know that this space is just a real Euclidean space of finite dimension. This is the dimension of this space. Okay, now I need to talk about Gaussian measures. Now this is a partition function. In the p-Adic framework, I'm going to suppose that the fields are elements of this Lee Sorkin space. In order to make sense of this integral, it is necessary to use discrete versions of this integral, like in the classical case. But in the p-Adic framework, it's very easy to construct a discretization of this integral. We just restrict the function phi to the space dl. Okay, so this is the discretization. Now, the key point is that this is a finite Euclidean space, exactly this space, and on this space we have a natural measure, which is a product of one-dimensional Lebesgue measures. In addition, this E0 is just this quadratic form. Then the discretization is just a classical Gaussian integral. So this is a definition. I'm going to define the discretization of this partition function in this way, where NL is a normalization constant. Now, we can compute this Gaussian integral. This is the result, and this is the normalization constant. Okay. Now I'm going to define a family of Gaussian measures. Okay, this is the definition. This is the normalization constant, exponential. This is a diagonal quadratic form, and this is the Lebesgue measure in this space. Now, if f is a function defined on this space, and A is a subset of this space, then we can, this functional makes sense. This is a linear functional if the function f is continuous and bounded. The next step is to construct extensions of this functional. Okay. In order to do that, I use the Kolmogorov consistency theory. Okay, let me read the result. There is a probability space and random variables such that PL is the joint probability distribution of these random variables. This space is unique up to isomorphisms of probability measure spaces. In addition, for any bounded continuous function f supported in this space, we have this formula. This formula says that these functionals, any functional of this form has an extension, and the extension is given by this probability measure. Okay? Now, the next step is to introduce this operator. This operator, the inverse, I mean, this operator is a kind of Euclidean version of the Klein-Gordon operator, but I'm working with the inverse of this operator. This operator is a pseudo-differential operator. This is the symbol of this operator. Okay. Oh, my presentation is stopped. Oh my. Okay. Now, the green function is, by definition, the inverse Fourier transform of the symbol. This is a distribution. Indeed, this is a real distribution. Okay. Now, with this operator, I construct a bilinear form. Given a pair of test functions, this formula gives a well-defined real number. Then this bilinear form is positive, continuous on this product space. Now, if in the particular case in which phi belongs to this finite dimensional isotropy space, this expression is a quadratic form. Indeed, is the quadratic form corresponding to the discretization of the functional E0. Now, the collection of this is the collection of all the restriction of the bilinear form B to a finite dimensional subspace of R. This collection is equivalent to this collection. In other words, and the second collection is determined by the discretizations of the energy functional E0. The point is that under suitable hypotheses, By determines a Gaussian measure or a Gaussian process. Under suitable conditions, it is possible to construct a Gaussian process by gluing all these processes, okay? In order to do that, I need the Wagner-Milnos theorem. The first step is to introduce a suitable Gelfand triple. This is the Gelfand triple that I need. So what is a Gelfand triple? This is a nuclear space because this is a subspace of the space of the test functions. It is well known that the space of the test function is nuclear. Every subspace of a nuclear space is nuclear, so this is a nuclear space. This space is dense in this space. This is a theorem due to Albeverio, Chelkovich, and Krennikov. And given a function in this space, we can construct a distribution. Now, let us consider this mapping. This mapping is a characteristic functional. This means that this mapping is continuous in the topology of this space, positive definite, and the value of this mapping at 0 is 1. Now, if we apply the Wagner-Milnos theorem, we get a probability measure P, depending on all these parameters. This measure is called the canonical Gaussian measure on this space. This is the Lysorkin space of distribution of the second kind, and B is the algebra of cylinder sets on this space. Now, this probability measure is determined by this formula. This formula says that the Fourier transform of this probability is this functional, okay, the functional C. Now, the key point is that the measure P is unitarily determined by this family of Gaussian measures. If we restrict P to Y, a finite dimensional space, we get a Gaussian measure on a finite dimensional space. If the dimension of Y is n, we have this formula. Notice that B is the operator constructed with the inverse of the Klein-Gordon operator. Now, I mean, in other words, or equivalently, P is uniquely determined by this family, okay? This probability measure is determined by this bilinear form. And I already mentioned that this family is completely determined or equivalent to this family. This is the family of bilinear forms constructed using the discretization of the energy functional EC. So this is the result. It is important that I need this condition alpha 2 greater than 0. The mass of the field is positive. Then this probability P is uniquely determined by this sequence. Remember that PL is the Gaussian measure associated to the discretization of the functional E0. And second, if we have a function on this least working space, which is continuous and bounded, then the limit of these functionals is exactly this functional, okay? In other words, the sequence of discretizations, this discretization determines the probability measure P in this space. Here is not is calligraphic L. Okay. Partition functions and generated functionals. Now, in order to construct interactions, I use a real polynomial. The key is a real polynomial. The key property is this. It is a positive, a non-negative polynomial. This is important to assure this condition. Each of these theories corresponds to a thermally fluctuating field, which is defined by means of a functional integral representation of the partition function. This is the classical interpretation. All the thermodynamic quantities and correlation functions of the system can be obtained by functional differentiation from a generating functional, as in the classical case. I'm going to assume that phi is an element of this least working space. I assume that phi represents a field that performs thermal fluctuation. I also assume that in the normal phase, the expectation value of the field is 0. So the size of this fluctuation is controlled by this energy functional. Now I'm going to include an interaction energy, and this is the interaction energy. This is the classical definition. But now we are working with, we are integrating on QPN.
Excuse me, can I ask you the question?
Go ahead, Igor.
Thank you. So E0, at E interaction you have. E interaction is translational invariance, as I see.
You are talking about this interaction, E0.
No, E interaction is translational invariance. My question is concerning E0. Is it translational invariant?
E0, yes. I mean,
but you have a lot of parameters, delta, gamma.
Yeah, okay. No, but this seems that is, I mean, there is a group, a subgroup of GL, of the general group, with coefficient in CP that, that is the group of symmetries of E0, of just E0. In that sense, E0 is translational invariant. There is a group that fits this function.
Usually in such case, there are volume divergences.
Yes, but yes. No, but the point is, yes, but it doesn't happen in the p-Adic frame. That's the point.
Can you comment why?
Yes. Give me a minute.
Okay, thank you.
Okay, so here, this is the definition. Now, this is the free partition function. Notice that I use E0. E0 is the energy functional defined using the kinetic term and the mass term to construct this probability measure. In the classical case, in the classical formula here, we have exponential of minus E0 evaluated at far. But I use that function to construct this probability measure. Now, the discrete version of this partition function is this integral. Okay. Now, the partition function in the general case, I mean, when we have interactions, is given or is defined by this formula. Notice that I am giving a definition. Okay. Now, this is the definition of the partition function with interaction, and this is the discretization. Now, from a mathematical perspective, a p-field theory is given by this probability. Notice that exponential of minus energy of interaction of phi is less or equal. I mean, this function is integrable with respect to this probability. Then this measure makes sense. In addition, notice that I'm working with test functions. For this reason, Igor, this is my definition. So this is a well-defined probability measure. You see? In addition, notice that I am not working with distributions. Okay, I am working with test functions. In this framework, this is a well-defined probability measure. Okay. Now, the endpoint correlation functions of the field are defined in the classical way. This is the definition. Notice that here I use the probability measure. This is the discretization. These are the discretization of the correlation functions. Okay. Instead of this space, we use this finite dimensional space. Instead of this probability, we use PL. Now I'm going to introduce a current, a source term, and this is the energy term corresponding to J. Now I get a new energy functional, okay? And this is my generating functional, okay? Now here I have the source term, okay? And this is the discretization, okay? To get the discretization, we pass from this infinite dimensional space to this finite dimensional space. We change this probability P by PL. Now, let me recall the definition of the functional derivative. The functional derivative of the generating function is defined by this expression. This is a directional derivative or a Gateau derivative. Okay. Now, this is a result. Suppose that theta 1 up to theta n are test functions, Lee-Sorkin test function. Then these functional derivatives of this functional derivative exists, and this formula holds true. Okay, so we have this formula. Notice that here we are integrating with respect to the measure P. Now, if you see here, we have this is the L2 product. If we replace this L2 product by its definition, we get some additional integrals. Now, in addition, the functional derivatives, this functional derivative can be uniquely identified with this distribution. This expression was obtained by replacing in this formula the definition of L2 product. So we can identify this functional derivative with this distribution in the Lee-Sorkin space. Okay. Now, in an alternative way, we can define the functional derivative, like in the classical case, as a distribution from this space. Now, in this second interpretation, we assume that this Gateau derivative we identify this Gateau derivative with the kernel of this distribution. Using this notation, we obtain that the functional derivative, this functional derivative of this degenerative functional is given by this expression, by this formula. But now this formula is valid as an equality between distribution in the Lee-Sorkin space. Now you see, if we put J equals 0 here, we get up to a suitable constant, we get the correlation functions of endpoints. This is the result. The correlation function of endpoints as a distribution is given by this formula. Notice that it was necessary to correct this normalization constant. Okay, now the free field theory. This is the proposition. Okay, Z0 is the generating functional of the free field theory. Is 0 here. 0 means that the parameter alpha 4 is 0, then there is no interaction. And this is the result. This generating function is given by this expression. J is the source. G is the green function of this operator. Okay? So the key point is if the source is a function in the Lizorkin space, this equation has a unique solution. This is the Fourier transform of this unique solution. In addition, this solution can be represented as the convolution of the source with the green function. Okay? And this is the demonstration of this result. We change variables, like in the classical case. We get another measure. It is possible, and then by we have to isolate this term. This is a constant, and we can rewrite this term in this way. It is possible to show that this is also, the P prime is also a Gaussian measure, but with mean different from 0. Okay. Now the correlation functions of the free field theory are evaluated in the classical way. Okay. But now this is a mathematical result. Now the perturbation expansion, the existence of a convergent power series expansion for the generating functional, the perturbation expansion in the coupling parameter alpha 4 follows from the fact that this function is an integral function by using the dominated convergent theory. So this is the idea. We expand, this integral contains exponential of an integral of phi4. By expanding this exponential, we get this expression. This is the end term of this expansion. Okay. Now, this is the final result. In the case of a phi4 theory, the endpoint correlations of the field phi admits the following convergent power series. Okay, this is the classical calculation in the p-Adic framework, but now this is a mathematical theory. Okay, let me discuss a little bit about the possible physical interpretations of these results. Now I'm going to consider this energy functional. Okay, this is the kinetic part. This is the mass part, the interaction, and consider a phi4 theory. And this is the source term. Now the parameters alpha, gamma, alpha 2, and alpha 4 are functions of the temperature. I'm choosing the classical. This is the classical supposition. Now, if J is 0, then we have this energy functional is invariant, and this transformation, this is a C2 symmetry. Now, there is also a translation invariance. More precisely, there is a subgroup of the general linear group with coefficients in ZP. Under this subgroup, this term is invariant. Okay. Now, I'm consider phi as a function in this space. I consider that phi is a local ordered parameter of a continuous Ising system with external magnetic field J. I also assume that J it belongs to this finite dimensional space. All the calculations in these sections are carried out in a finite dimensional space. The system is contained in this ball. We divide this ball into sub-balls or boxes. Okay. The volume of each of these balls is p to the minus L times L, and this is the radius. Phi I represents the average magnetization in this ball, okay? And this is the representation of the order parameter in this space. Is a locally constant function. This is an important observation. Notice that the distance between 2 points in this ball is less than or equal to p to the minus L. Then this function varies appreciable over distances larger than p to the minus L. Okay? These observations are also true in the classical case. Now, I'm going to consider this partition function in the finite dimensional case. This is just a sum, and I'm going to consider that this is the partition function of continuous Ising mode. The next step is to compute the minimizers of this functional. Okay, the minimizers of this functional are the constant solutions of these equations, really are the solutions of phi. In order to establish this result, I use Lagrange multipliers because I am working in a finite dimensional space. So this is just a classical minimization problem, okay? So the solutions, the minimizers of this energy function are the constant solutions of this equation. So if you see this equation, we have 3 solutions at most, okay? Now this is the classical interpretation. If J is 0, the field the field phi is a minimum of the energy functional E if it satisfies phi. Then if the temperature is greater than the critical temperature, we have that alpha 2 is greater than 0, and the ground state is 0. In contrast, if the temperature is less than the critical temperature, then alpha 2 is negative, and there is a degenerate ground state plus minus phi0, where phi0 is given by this formula. This implies that below Tc, the system must pick one of the 2 states, plus phi0 or minus phi0, which means that there is an spontaneous symmetry present. I'm going to stop here. Thank you very much for your kind attention.
Okay, thank you, Wilson, for very interesting talk. We have time for questions or comments.
Okay, can I ask a question?
Yes, please.
Yeah, Wilson, thank you for a very impressive talk. I have a question about, please show your